Welcome to Learn with Us. This is the 30th and last lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you solved some examples related to MOSFETs, and you also understood the difference between two types of transconductance parameters. First type is process transconductance parameter, and second type is MOSFET transconductance parameter. What are the learning objectives of this lecture? In this lecture, you will understand conductance of channel. You will study how MOSFET acts as a linear resistance. In this lecture, you will also understand how MOSFET acts as a capacitor. Now we will understand the conductance of the channel. The conductance of the channel can be found by using this equation where mobility of electrons is multiplied by capacitance of oxide layer and it is multiplied by transistor aspect ratio, and here we have gate to source voltage minus threshold voltage. We know that effective voltage is equal to gate to source voltage minus threshold voltage. So now this equation of conductance becomes mobility of electrons multiplied by capacitance of oxide layer, and here we have transistor aspect ratio, and now here we have effective voltage. We know that this term is process transconductance parameter. So the simplified form of this equation becomes K dash multiplied by transistor aspect ratio, and here we have effective voltage. So this is the conductance of the channel. Okay. The MOSFET behaves as a linear resistance RDS when drain to source voltage is kept small and the value of this resistance is controlled by the gate voltage VGS. The formula of this resistance is RDS is equal to 1 divided by conductance of the channel. We know that the equation of conductance of the channel is this. Here we have VGS minus VT, okay, and we can write this equation like this, okay. Now we know that MOSFET transconductance parameter is given by this equation. It means 2K is equal to this term. Now we can substitute this value here in this equation. So this formula now becomes 1 divided by 2K effective voltage. Okay. Now look at this example for a MOSFET with aspect ratio 8 micrometer divided by 0.8 micrometer, and here the value of resistance is 1000 ohms, and the value of process transconductance parameter is 194 microamperes per volt square. Okay, and here threshold voltage is 0.7 volts. Okay, now if you want to find the value of effective voltage and gate to source voltage, so how you are going to find these unknown values? We know that the formula of this resistance is 1 divided by mobility of electrons multiplied by capacitance of oxide layer, and here we have aspect ratio, and here we have gate to source voltage minus threshold voltage. We know that this term is process transconductance parameter and this is effective voltage. So this equation can be rewritten as okay. Now here this effective voltage is unknown. So if we rearrange this equation, we get effective voltage is equal to 1 divided by process transconductance parameter multiplied by aspect ratio, and now here we have this resistance. Now we put all these given values here. This process transconductance parameter is 194 into 10 raised to the power minus 6, and this aspect ratio is 10, and the value of RDS is 1000. Okay, now after solving this you will get 0.52 volts. Okay, so this is the value of effective voltage here. Now we will find gate to source voltage. We know that effective voltage is equal to gate to source voltage minus threshold voltage. If we rearrange this equation, we get gate to source voltage is equal to effective voltage plus threshold voltage. Here effective voltage is 0.52 volts and threshold voltage is 0.7 volts. After adding these two voltages, we get 1.22 volts, which is the value of gate to source voltage. So this is your answer. Now look at this example. If you have a capacitance of oxide layer 8.6 into 10 raised to the power minus 3 farad per meter square. If mobility of electrons is 450 centimeter square per volt second, and here threshold voltage is 0.5 volts. If gate to source voltage is 1 volt and resistance is 1 kilo ohms, and if you want to find the required value of channel width here when minimum length of channel is 0.18 micrometer, so how you are going to find this value here? Again you will use this formula of resistance, which is equal to 1 divided by mobility of electrons multiplied by capacitance of oxide layer, and here it is multiplied by this transistor aspect ratio, and here we have gate to source voltage minus threshold voltage. Now after putting values here, this term is equal to 388 microamperes per volt square, and here we have W divided by 0.18 micrometer, and here after solving this term you get 0.5 volts. Okay, we know that the value of resistance is 1 kilo ohms, and here we have 1 divided by 388 microamperes per volt square, and here we have W divided by 0.18 micrometer, and here we have 0.5 volts. Now if we rearrange this equation, we get W is equal to 0.18 micrometer divided by 388 microamperes per volt square, and it is multiplied by 0.5 volts, and here we have 1 kilo ohms. Okay, after solving this you will get 0.93 micrometer, which is the width of the channel. So this is your answer. Now we will understand how MOSFETs are used as capacitors. There are four types of capacitances of MOSFETs which exist in both N-type and P-type MOSFETs. First type is CGS, which is gate source capacitance. Second type is CGD, which is gate drain capacitance. Third type is CSB, which is source to bulk capacitance, and it is also called source junction depletion capacitance. And fourth type of capacitance is CDB, which is drain to bulk capacitance, and it is also called drain junction depletion capacitance. Okay, so these are the four types of capacitances that are present in MOSFETs. Now look at this figure. As you can see here, this terminal is source, this is gate, this is drain, and this is bulk. So gate to source capacitance is present here between source and gate terminals, and gate to drain capacitance is present here between gate and drain terminals, and here this source to bulk capacitance is present between source and bulk terminals, and this drain to bulk capacitance is present between drain and bulk terminals. Now we will understand capacitances in all three regions of operation in MOSFET. First we will talk about saturation region. In saturation region, gate to source capacitance can be found by using this formula, where this is width of channel, this is length of channel, this is capacitance of oxide layer, This is overlap capacitance. This overlap capacitance is due to overlapping of gate on source and drain. This overlap capacitance is equal to capacitance of oxide layer multiplied by area of overlapping. Okay. We know that area is equal to width multiplied by length. So we can write this equation like this, where this is length of overlapping. Okay. So now this formula of gate to source capacitance can be written like this. Here I have substituted this value of overlap capacitance here, and here we have this area of overlapping. Okay, so you will use this formula to find gate to source capacitance in saturation region. The formula of gate to drain capacitance in saturation region is this. Again, if we put the value of overlap capacitance here, then the formula becomes 1 by 3 WL capacitance of oxide layer plus capacitance of oxide layer multiplied by area of overlap. Okay. Again here this area of overlap is equal to width multiplied by length of overlapping. Okay. The formula of source to bulk capacitance in saturation region is this, where this is capacitance of source junction, this is area of source, and this is area of channel at source side, and the formula of drain to bulk capacitance is this, where this is capacitance of drain junction, and this is area of drain. Okay, so these are the formulas of capacitances in saturation region. Now we will understand side wall capacitance. Here first we will talk about source side wall capacitance, and then we'll talk about drain side wall capacitance. Okay, now look at this MOSFET configuration, and here it is like this. Okay, now this is gate, this is gate, this is source, this is drain, and this is source. This is of n-type, this is of n-type, and this is of n-type. Now look at this region only. Here, drain sidewall capacitance will be here, and source sidewall capacitance is here. Okay, so the formula of source sidewall capacitance is this, where this is sidewall junction capacitance, okay, and this is source perimeter, okay. The formula of drain sidewall capacitance is this. Again, as you can see here, we have sidewall junction capacitance, and this is drain perimeter, okay. These PS and PD perimeters, their unit is micrometer, okay. Now in case of sidewall capacitance, the formula of source to bulk voltage in saturation region is this. It means here this source sidewall capacitance is added. So now this formula becomes this, okay. Now what about drain to bulk capacitance in case of sidewall capacitance? Its formula is now written like this. It means here this drain sidewall capacitance is added. Now if we put the value of this drain sidewall capacitance here, this formula looks like this, okay. So these are the formulas of source to bulk capacitance and drain to bulk capacitance when there is sidewall capacitance. Now we will understand capacitances in triode region of operation. The formula of gate to source capacitance in triode region is this, and here we have overlap capacitance. Again, this overlap capacitance is equal to capacitance of oxide layer multiplied by area of overlap. It means this formula can be written like this, plus capacitance of oxide layer multiplied by area of overlap, okay. Now here the formula of gate to drain capacitance in triode region is this. As you can see, this formula is same as this formula of gate to source capacitance. It means here gate to drain capacitance is equal to gate to source capacitance. Okay. Now here the formula of source to bulk capacitance is this. Okay, without sidewall capacitance. If there is sidewall capacitance, then we add source sidewall capacitance here. It means now this formula of source to bulk capacitance becomes this. Okay, the formula of drain to bulk capacitance in triode region is this without sidewall capacitance. In case of sidewall capacitance, drain sidewall capacitance is added here, which is this. Now if we put the value of drain sidewall capacitance here, this equation becomes this. Okay, so these are the formulas of capacitances in triode region. Now we will talk about cutoff region. In cutoff region, the formula of gate to source capacitance is this. It means here gate to source capacitance is equal to overlap capacitance. We know that overlap capacitance is equal to capacitance of oxide layer multiplied by area of overlap. It means here this gate to source capacitance is equal to capacitance of oxide layer multiplied by area of overlap, and we know that this area of overlap is equal to width multiplied by length of overlap. Okay, now the formula of gate to drain capacitance in cutoff region is this. As you can see here, this formula is same as the formula of gate to source capacitance. So it means here gate to drain capacitance is equal to gate to source capacitance. Okay, the formula of source to bulk capacitance in cutoff region is this without source side wall capacitance, and in case of source side wall capacitance here this term is added, and we know that this is equal to this term. Okay, now the formula of drain to bulk capacitance in cutoff region without side wall capacitance is this, and in case of side wall capacitance here drain side wall capacitance is added, and we know that this drain side wall capacitance is equal to this term. Okay, so these are the formulas of capacitances in cutoff region. Okay, now look at this example. For the given data, find the four capacitances in cutoff and triode region of field effect transistors if Width is 90 micrometer. Length of channel is 0.8 micrometer. Area of source is equal to area of drain, and they are equal to 100 micrometer whole square. Here source perimeter is equal to drain perimeter, and they are equal to 102 micrometer. Here overlap capacitance is 3.9 into 10 raised to the power minus 4 picofarad. Here capacitance of oxide layer is 3.3 into 10 raised to the power minus 3 picofarad per micrometer square. Here junction side wall capacitance is 1.5 into 10 raised to the power minus 4 picofarad per micrometer. Here source junction capacitance is equal to drain junction capacitance, and they are equal to junction capacitance, and they have the value 4.4 into 10 raised to the power minus 4 picofarad per micrometer square. Okay, now first we will find capacitances in cutoff region. We know that in cutoff region gate to source capacitance is equal to overlap capacitance. It means here this gate to source capacitance is 3.9 into 10 raised to the power minus 4 picofarad, and here in cutoff region gate to drain capacitance is equal to gate to source capacitance. It means here this gate to drain capacitance is also 3.9 into 10 raised to the power minus 4 picofarad. Okay, now we will find the value of source to bulk capacitance in cutoff region. We know that its formula is this. Okay, now we will put values here. We know that this source junction capacitance is 4.4 into 10 raised to the power minus 4 picofarad per micrometer square, and this area of source is 100 micrometer square. Here we know that this junction side wall capacitance is 1.5 into 10 raised to the power minus 4 picofarad per micrometer, and this source perimeter is 102 micrometer. After solving this, you will get 0.0593 picofarad. Okay, now we will find the value of drain to bulk capacitance here. The formula of drain to bulk capacitance in cutoff region is this. Here we know that the values of source junction capacitance and drain junction capacitance, they are same. The values of source area and drain area are also same. This term is fixed, and the values of source and drain perimeters are also same. It means here the value of drain to bulk capacitance will be 0.0593 picofarad. Okay, so these are the capacitances in cutoff region of field effect transistor here. Now we will find capacitances in triode region of field effect transistor. we know that the formula of gate to source capacitance in triode region is this. Here we know that width is 90 micrometer, length is 0.8 micrometer, capacitance of oxide layer is 3.3 into 10 raised to the power minus 3 picofarad per micrometer square, and here this overlap capacitance is 3.9 into 10 raised to the power minus 4 picofarad. After solving this, you will get 0.119 picofarad. So this is gate to source capacitance here. We know that in triode region, gate to drain capacitance is equal to gate to source capacitance. It means here gate to drain capacitance is also 0.119 picofarad. Okay. Now we will find source to bulk capacitance in triode region. We know that the formula of source to bulk capacitance in triode region is this. Now we will put values here in this formula. We know that this source junction capacitance is 4.4 into 10 raised to the power minus 4 picofarad per micrometer square. Here this source area is 100 micrometer square. We know that area of channel is width of channel multiplied by length of channel. It means here we have 90 micrometer multiplied by 0.8 micrometer divided by 2. We know that here the value of junction side wall capacitance is 1.5 into 10 raised to the power minus 4 picofarad per micrometer, and here the value of source perimeter is 102 micrometer. After solving this, you will get 0.07514 picofarad. So this is the value of source to bulk capacitance here. Now we will find the value of drain to bulk capacitance. We know that the formula of drain to bulk capacitance is this. Now here we know that the values of source junction capacitance and drain junction capacitance are same. The values of source area and drain area are also same. This term is fixed here. This term is also fixed, and here the values of source and drain perimeters are also same. It means here the value of drain to bulk capacitance will be 0.07514 picofarad. Okay, so these are the values of capacitances in triode region of field effect transistor here. Okay, now here is your class task. For the given data in last example, find the values of all four capacitances in saturation region of field effect transistor. Okay, that's all for today. Now what are the key takeaways of this lecture? In this lecture, you studied how MOSFET behaves as linear resistance. You also understood how MOSFET acts as a capacitor. In this lecture, you also studied about four types of capacitances that are present in all three regions of operation in MOSFETs.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.